Good morning, students. So this is a session we're going to talk about that is the GATE training program. So it is in the banner of AICTE Parano. So today's subject is database management system. The topic is file indexing. So in that subtopic is B plus 3. That is we're going to discuss. So yearly class, that is I have explained what is a file indexing, what is a B tree. So this is the session that is a B plus 3 we going to talk. Okay. So overall idea about that I'm going to explain. So what is called B plus 3? So what are the operations we can done? How to make a hierarchical of your tree? So what are the nodes we can insert, delete, and we can update in this tree? So it is based on the tree structure. You all know that is a tree mates, branch, nodes, edges we going to see. So that is a basic concept only. So this is not only a new concept, it is derived from the data structure. So it is implemented in the database management system. Is that clear? So this is the first I want to take. So that is a database system. It is used for storing a data. So in a disk, okay, it may be a disk is based on your storage system. So it is a consideration for that is a different systems we can use for storing a data. So that is the hard disk. Okay, secondary device, primary device called it as a RAM. So it's all will be having your some access method. So how we are storing a data, how we are retrieving a data. So that is a sequential access method, a random access method, so file access method, hierarchical access method. Lot of methods are available. In that, that is a ISAM. Okay. So ISAM, it is the meaning of indexed sequential access method. So that is indexing is a very important when we are handling a file. Okay. So that is I give you an example. First, that is the to take it as a book. Okay. So it is a lot of pages available in our book. So why we are having a index in front of that every chapter or maybe every book is a first or two second page or third page we having an index. So it giving the clear access and it is easy to view the data which is available inside of your book. Same thing. So indexing method it is give the opportunity to the data accessor to view and quick accessing your data. So that is the indexing concept. It is the same procedure they are following. So it is ordering in a sequential manner. So it may be a alphabet order or maybe chapter in your numerical order or it may be it is the how that is a content we having. So it is the example of book if they having your indexing of sequential order. Same thing we having your inside of your computer or we having your hard disk or maybe your any other storage devices we can use this method as a ISAM that is indexed sequential access method. Clear? Okay, so let I explain. So M-way search trees. So M-way search tree, so that is the one of the way we can use that is a search tree. The next B trees. B trees are the another way that can be search your node from your hierarchical of your data. Okay. So let I explain. It's a data layout on your disk. Okay. So this is see this architecture. Okay, how the disk will be available. So inside of your every hard disk. Okay, so track, sector, block. So track means each and every hard disk by a track. So that is the one ring shape we have. So see this diagram. It shows that is a track. Sector means that is a piece of that particular partition area. Okay, that we called as a sector. Okay, so that is shaped like a piece. See that? So this is the your sector. Okay, so next this is the block. So intersection of your track and sector we call it as a block. So this is the important keywords each and every storage system they following. So this is a data layout on your disk it shows. Okay, it's clear, students. It's a clear to you all. Okay, thank you. So next, that is the concept. So disk log access time. So how long it's going to take. So it's storing a data and as well as accessing the data. So this we call it as an latency. So that is a disk block access time. So we can do the some of the formulas we can use to see how that is the access time will be calculated. Okay. So that is the seek time. It is a maximum of so time for a disk head to move to correct track. So that we call it as an seek time. So what is the time taken by the your head? Head means nothing but if you have in your hard disk, it is the sensor available. It's a read the data from the disk and it's a write the data to the disk. So how long it's going to take so to move the correct okay so into the your hard disk. So this is we call it as in seek time. So here it is nothing but it is a sensor. It's available inside of your hard disk. Okay, there's a laser sensor available. Sometimes there is a latency they can use. So some authors can use latency as a term of its component. So this they use the latency to refer to all of what we are calling this time. So latency time, seek time. So it is a both are interchangeable words. Clear? So that's sometimes they call latency time, sometimes called that as a seek time. This is a head. So it's a time taken by the your hard disk head to move the your head into the correct track. Okay, it may be a take is a millisecond, it may be a take nanosecond. So nowadays that is your system will be i5 processor, microprocessor, heavy microprocessor. So there's a new hard disk, SATA hard disk, like all these advanced hard disks are available. So head movement also that is a microprocessor, RAM processor also it will be a so very good because of that. We not have a feeling that is the how it's a loading time. If we cannot, there is a feeling that it's a previous 10 years or 15 years, 13 years back. It is a very difficult when you are clicking a data, it will be taking a time. When you are storing a data, it is taking time. When you are accessing a data from your hard disk, it's taking a time. So this is all the new technology and accessing methodology. It is a giving the so access in a good manner. Its efficiency of the access will be increased by of the technology of the hardware. Next, that is a transfer time. It's a time to read or write the data. So that is approximately is a time for the sector to spin by the head. Okay. So this is the time. Okay, that we call it as a transfer time. So once again, it's a time to read or write your data. That is a transfer time. Okay. So you take it the your RPM. There's a rotation per minute that we call it as an RPM. So for it to 7,200 RPM hard disk with the 8 milliseconds seek time, average access time for a block is amount of 2 milliseconds. It is a formula. What we are talking about that is a formula that using that we can get this values. Okay. Next consideration for disk based directory structure. Okay. So is use of disk based method. So use of disk based method. Hello students, my voice is audible. Yes, yes, yes. Okay, thank you. So use your disk based method. So when your directory is too big to fit in a RAM at once. Okay? So such a case, that is the RAM will be a very important role player in this disk-based directory structure. Okay, so disk-based method it is used to that is the develop your tree. So then is in the dictionary formation, it is a too big to fit in the RAM at once. So for that consideration, so minimize the your worst case number of disk access for the essential operation. So we can use that as some of the methods. So put method, get method, remove methods are available. So for this is a scenario, we are looking for here some of the formulas or some of your access method that we call as a keep space requirement responsible. That is the big O of n. Okay, this is the concept. That is the very simple concept, big O of n. So it is the method is based on binary tree, so such as AVL. Okay, so AVL search tree, so are not optimal for disk based representation. So the number of disk access can be greatly reduced by using the M-way search tree. So in the beginning of the slide, I have told that is the we are talking about your B tree and B plus tree in the concept of M-way search tree concepts only. So this is the our motto. So the our problem is when we are using the previous concept is a dictionary concept or access method. It is a very large and it is a very big, and it cannot be fit into the RAM. So to minimize this kind of worst case, there is a lot of essential operation we can use. That is a put, get, remove method all. So this also is not enough to manage this kind of structure, particular dictionary structure. So in a disk management concept, so that is a big O of n can be a responsible or is a consideration for this. So is a based on a B tree or binary. This a B tree means a binary tree. So such a that is the AVL search tree, not optimal for a disk based representation. So that is a better representation required. So binary tree also it's a B tree is also not enough. So that is the reason we are moving to the B plus tree. That is it, B plus tree, binary plus tree. So it is greatly reduced by the M-way search trees. Okay. So why we are using this access method is of finding a data in a group. Okay, in a collection. So from that, what we are looking that is a getting into the user. So that is the way this kind of mechanism is working. So B plus is a solution for this problem. Okay, clear? So what I'm talking, it is understandable. Okay, okay, thank you. So now that is the first concept I am going to explain. Bus method it belongs to the B plus tree. Okay. So same structure as a B tree. You all know that is the last class we have seen that is a B tree. The same structure here also we following. So next is dictionary pairs. Okay, leaves and right leaves, left node, right node. That is a concept. So here leaves from the W linked list. Okay. So you know that concept of linked list is direct from the data structure only. So that is the basic data structure concept. It's a W linked list based leaves we are going to use. Okay, these are dictionary pairs are leaves only. It's a very simple to implement because of that linked list we are selected. Okay, so next is remaining nodes have the following structure. See this J K K1, K2, and into the that is the last one. There's a KJ. Okay, so 0, A1, A2, A3 like that. So that is the so leaves and the your remaining nodes. Leaves and nodes will be structured in this way. So you can use any type of hierarchical or maybe sequential. Okay, so this is that is the identification purpose I used here. That is the so K1, K2, KJ. So that is the A1, A2, A3 like that, and so on until the J. Okay, so this is the node structure. So next J, what is J? You may think okay now that is a J is a number of keys in a node that we call it as a J. It's a number of keys in node that we call it as a J. So key mean that is the, your access value, or maybe access key, or access input, or maybe what your data is you are looking for, that we call it as a key. It is we call it as in symbolically J. So A is a pointer to a subtree where it is available. So where is the memory address? What is the access point of that particular node or in a subtree, that we call it as an AI. So clear, students? Okay, this is the important terms that will be reflected in the upcoming classes. Because of that, I am two times repeating this. Okay, so J is a number of keys in a node. So AI is a pointer to your subtree. The sequence order, you can name it any. J means I can, you can put A, you can put B. So these are the variables, you can change it, but it is sequential and the meaning is the same. So clear? Okay. So now I am moving to the next one. So last one, that is a K. So it is smallest key in a subtree. So it may be less than or equal to smallest key in subtree A and the largest number. So it is the greatest to into the AI minus 1. So this is a formula. Using that formula, you can construct a subtree, and you can calculate the path of traveling path of your node. Okay, so how long it's going to take you to reach your root node. So this is the way to we can find the access time of your particular data in your hard disk. So clear, this is the way of to. So our aim is to access the data in a simple way and in the minimum time. Okay, for what is the purpose we are using the B plus tree. Okay, so first we will take up the B tree example. Say m equal to 5. Okay, so I already told m way search method we following. So see this, so linked list. Okay, so that is three lists we having. So first one, that is the in that, so I having a two, the root has been 2 and the m children's. Okay, so 2 and m children's, that is a we having two links are we having. So that is the each non root internal node as between the m divided by 2. So that such a case, that is the m children's can be easily find. So in the same way, we can find the all other nodes which is available in a tree. So particularly B tree you're talking. So B plus tree is the same following, it's going to flow. So that does it see that there's a 2 and 3 and 8 will be available in a linked list. In the right hand side of the node is a 13 and 27 is the list that is linked to the your root node called 2. So all extra nodes are added in the same level. Okay. So extra nodes are is nothing but is actually it's a represent the null pointers in your implementation part. So this is the way this a B tree will be constructed if the value equal to m equal to 5. So same way we can construct a tree in a B plus. Okay, say example. Now that is the B plus I am talking. It's the same thing. So what I explained B tree. So last class also I explained B tree. So just recalling purpose, I can uh, tell this concept, that is the B plus tree. So that is the now that is the some example. So we can see in the B plus and B plus plus. So now that is the root node is in this diagram. You see this clear. There is a green color I mark it. So that is a 9. It is a root node. In the left to first left leaf node is a 5, and the right node is a 6. Okay, so 16. Okay, this is the two things are available. So we take it the, that is the first one, that is the 5. That is a left node, that is a 13. Okay, so next one is a yellow color market. So why I mark it, that is the green color nodes are so marked as a indexed node. So which are the available leaf node, that is the least most in the hierarchical, that we call it as a leaf node, or maybe in data management system we can use that as the data node. Okay, so clear, that is the index node, and then followed by that is the yellow color symbol. It is a to differentiate from the your hierarchical order. Because of that I noted is a leaf node is a yellow color. It is maybe also called as a data node. So clear. So this is the architecture for the B plus tree. So how it will be accessed from the leaf to the root. So what is the traveling time? So what is the minimum traveling time for to access the data from your leaf root to leaf? Okay. So this is our aim of this class. Okay. So take it. That is the key equal to 5. Now that is the assume that is already we seen that is m equal to 5 in the B tree. So now that is a key. So key is the your access pointer that will maybe used to access the value. So that is the now that is a given value will be a pi. Okay. So see that that is the 6 or less than or equal to key, or maybe next one key less than or equal to 20. That is the our condition. So first I want to check it is the 6 is the your least number. So then followed by equal to key. So that is the your 6 is not equal to that key value, so it will be a lesser values. Okay. So coming to the second one, that second condition will be fit to our part. So that is a key less than or equal to 20. So that key is a 5 value, it is a less than to the 20, so we can consider the second condition. So we will travel this path where it is available in that. Okay. So key equal to so 5, so that is a less than or equal to 20, it is a condition is true. So way in this such a way the algorithm will be executing so that we can traveling in that path. Okay. So now that is the insert 10. Okay. So insert 10, how can we insert here values in a b plus tree? So now that is the I'm going to insert a 10. Okay. So if I want to select which one is the least way, least path to insert this value 10, where I can include. Okay. So insert that is the 10. Okay. So insert 9 and 5 is your nodes, then followed by. So I want to make it that is the root node is a 9, and will be a leaf nodes or data nodes is a 1, 3, 5, 6, 16, 17, 13. So I can use that is the right side. So your data leaf node, then followed by you can add one data from that node. Okay. So you can make it this as a leaf or maybe a any other subtree root node. Okay. So such a we can add or insert here. So some of a leaf or maybe a data node inside of your tree. So insert a pair with a key 2. That is the last one is a key with equal to 5 we included. So now that is a key equal to 2. So a new pair goes into the third node in the list. So that is a third node. So that I can use that is the right side of your node 5. Then that is the your 1 comma 3 is the your pair. So that is the so it goes into the 3 node of your tree. Okay. So insert here node 3. So we have to look at in the some of the important thing. The first one, insert a new pairs so that the keys are will be a ascending order. That is a very important. So key will should be ascending order. Then only it will be we are following the sequential method. This is a sequential method. Sequential within the ascending order. Okay. So 1, 2, 3 or A B C D. See any keys that will be a following that is sequential order. So the first slide itself I told that is sequential order we following, so that this access method will be also following the some sequence. Here we following the key value will be 1, 2, 3. So such a way that is a key new pairs also keys are will be ascending order will be a important thing. So that is a 1, 2, 3 is a leaf node. So for that split into the two nodes. Okay. So know that that is the one is the another one node, and this 2, 3 is the another leaf node. Okay. These are two sets we have splitted. So from that is insert the smallest key in the new node and pointers also inserted. So that this is a way we can use the new node insertion into the parent node or maybe a root node. Okay. So you decide it will be available in the subtree or maybe a subroot node, or inside of that you having the leaf or be from the branch to leaf, that will be decided based on the your the depth and the width of your tree. See that that is a taken into the 2. So then that is a left side, I put it into the leaf 1, and right side I put it into the 2 and 3. So this is the way you can implement. Mostly right side will be, it will be having the more nodes, more data nodes, and left side part will be a lesser number that we having the access will be reduced. So this is the scenario we following the database management system with the tree or hierarchical access or maybe sequential access. So mostly that is the first right, then it goes to the left. Okay. So now insertion. So now already is a left hand side, that is a 5 is available. So now there is a 2 and 3. I have to include. So how I include, that is already is a 5 is available in the left hand side. So such a case, that is a 1 is the already leaf node of the 5. So that is the insert your index entry 2 plus a pointer into the parent value. So that is a 5 plus 2 maybe is going to include. So that way that is a 5 and 2 will be available as a parent node for a root node 9. So that again I want to include 2 and 3. So previously you see that, so that a 5 and 6. So 2 will be considered as here in the left hand side root node. So 5 comma 2, then 2 and 3 will be a leaf node for this hierarchical order of your root node 9 and parent node of your 2 and 5. Then it is the leaf node is now, there is a new leaf node for this 2 and 3. So 1 and is a set 2 3 and set 5 6 will be called as a pair. Set and pair will be the same meaning. Okay. So this is the insertion of your hierarchical or maybe a B plus tree architecture. So now that is insert a pair with the key 18. Okay. So now 18 means it's coming along with the your right hand side, because the values see that 16, 17, 30, 40, 16, 9. This all will be a collection of values which is available in the right hand side. So we call it as in key equal to 18. So automatically, so see that 16 and 17 will be a sequential numbers. Once again repeat, we following sequential access, because of that we following this order. So if the random sequential or random order, we following same different concept. So I am following sequential, because of that I am following these formulas. Okay. So 6 and 17. So it may be in bit, it comes followed by the 16 and 17. So leaf node may be a followed by 16, 17 and 18. Okay. Now our target will be 18. The key value will be 18. So such a way. So 17 it goes as a parent node. Okay. So now that is a 16 and 17 pair will be a segregated, and parent node, now that is the 16 13 is a parent node for this hierarchical order. Now I am making the 17 as a parent node now, because as a 18 will be a key. So there's a insert a index for the entry 17 plus in the pointer table and as well as into the parent hierarchy, so that I can add the parent node 16 comma 30. In between 16 and 30 we can add a another node. So 17. So now I make it as a 30, 17, 18, 30, 40. So this hierarchy will be made. Now I am going to add the 17 followed by 16, 7, 16 comma 17. This is the now new parent node. Okay. See this. So previous one. So 16, 30. So 9, 16, 17, 30 and 40. So now that is a becomes 17 and 18 will be a leaf node. So I added the pointer to the parent node of the 17, so that now that is a 16 will be a one node. So for a parent node, and that will be parent node. Now that is segregated. So then followed by that. So now that is the leaf node will be a, so 7, 16 it is a belongs to 16. So 13 it's a belongs to the, that is the, so 17, 18 and 30 and 40 it's a belongs to the parent node of the 30. Okay, now it is insert a key pair is a value equal to 7. Okay, so it is the left hand side of the your hierarchical order. Same thing we following for this procedure. So we getting the value, that is a, we getting a final tree. So like that we going to get the final tree. Clear? So yellow splits into the 5 and 6 and 7. So index entry 6 is inserted into the parent. So parent is splitted into the 2 or 3 tree. The grandparent is splitted into the roots and as well as the root hierarchical leaf. So this is the highest increase by the 1. So this is the way of we can increase or maybe insert here nodes and leaves and parent inside of your tree. Okay, so B plus tree. So this is insertion, then followed by deletion. So if I want to delete some node in the hierarchical of this tree, so that is a branch you can delete. You can delete the parent. You can delete the leaf. But we having this some procedure. If you delete parent means you have to delete before the leaf. So leaf deleted only we can branches can be deleted. Okay, directly you cannot do that process. So that is the deletion is a necessary for necessary. So it will be start from the leaf node to the root node. Okay, that is a procedure we have to follow. Okay, so delete pair with the key 16. So where it is 16 is available. So in the root node 9, in the branch parent node that we call as 16 and 30. So then it's a leaf will be a 16 and 17 will be a leaf in this hierarchy is a right hand side. So least most leaf will be 16 and 17. So before that we having this 9. Okay. So delete pair is always a leaf. Okay. The delete pair is always in a leaf. So such that is the delete pair. It will be starting with the 16 and 17. So now that is 16 is a deleted. So that is the maybe is a barrow from the one pair of the siblings, and is a balance size of the different mode can be sibling. Okay. So this is the way we can tell. So delete pair with the key one. Okay. Next one. So now that is a pair will be a one. We say here that is will be a right hand side. It's not available one. So we go to the left hand side a branch. So 2 comma 5 that is a leaf will be a 1. So that is the key equal to 1. So we take it as the so get the values that is if that is your value will be less greater than or equal to 1. So we have to check. So adjustment sibling and is update parent key in the hierarchical order. Okay, so that we can do that process. Okay, so that is a 1 will be deleted so that I'm making is a 3 is the branch and then 2 and 3 will be at different leaves. Okay, so with this condition I make it this one. So next one that is a delete pair with the key 2. So same thing is going to happen inside of the left hand side hierarchical. Okay, left hand side that is a 3 comma 5 will be a lower parent node. In third that is a first leaf will be a 2. So that how we matching that is a less than or greater than or maybe equal to we have to check. So 2 is available. So that merge with the sibling, delete in the between the keys in a parent so that we can make delete the nodes or maybe a leaf in the previous tree. So this is the one 2 will be a deleted so that okay. So 3 will be a becoming a leaf node, then 5 only now available as a parent node, then that is the our rightmost side of the f 5 will be 5 comma 6. It is the data node. So now that is will take it is a pair with the key 3. So that is a 3 will be a deleted first one. Okay, so 3. So now that is the second I want to check the condition. So this is the greater than or equal to 1. The sibling is updated in the parent. So now that is the your 3 is a deleted. Now that is the highest number in this right hand child is a 5 6. So that is a 6 now is a becoming a parent node. Then is a 5 and 6 will be considered as a leaf node. So our data node in this hierarchical order. So such a way you can delete the leaf node, then you can delete the your parent node. So delete the pair with the key 9. Okay, now I am coming to the right hand side. So now that is the 9 is available. So that is the now 9 deleted means we have to consider all the comparisons of this. So merge the sibling and delete in between key in the parent. So that case 9 is deleted and the sibling the case in between. So such a case that is the 17, 30 will be becoming your parent tree now. That is 70. Then that is the 30 will be available. So that between what we number having, that is 16. So 16 will be deleted over here. So that is 30 will be your parent meal. 17 will be your right leaf, and left leaf will be a 17, and right leaf will 30, 40. So next one, that is a delete pair with the 6. Okay, so now that is a 6 is available. So now 6 sibling is a way to delete the between key parent. So that is a parent is a deleted. So 5 will be a becoming is a index node becomes a definitive. Okay, so that is again I want to check the greater than or equal to 1 the sibling. So move is the last one parent, get the parent. So that is the way you can use this. So this will be order will be a change. Okay. So delete 9. So that says that sibling. So merge sibling is a delete in between the key and the parent. So then followed by that is the values. So same, that is index node is a different from the merge data nodes. Okay. So deficient is available. So the index node is a between deficient. Let's see this. Okay, so merge sibling with the in between the key parent. So now that is the all will be deleted. So 16 and 13 are only available as a parent node. So same, that is the node becomes deficient. So that is it is a root is a discarded. Then is a b plus 3 will be from this one. So that is the m equal to 3. So make it is a formula root as a between 2 and 2 star floor. So that is the 2 m minus 1 whole divided by 3 plus 1. Okay. So it is a lower bound is the same as the b plus 3 and b3. So m equal to b and m equal to 4. So that is a b3 allows that is a nodes with the degree of 2, but is a b plus 3, so needs to allow the degree of 3. So I assume that is a greater than 3. So further things will be need to delete it. So that is a flat node need to support a insert and delete and improve the worst case search time and expense of the insert and delete useful when you are using the your b plus 3. So using this, you can easily delete the children's node, then followed by the your parent node, then the your root node. Okay, clear? So the remaining nodes will be between the m minus 1 all divided by 3. So if we consider the m is a children, using this formula, you can delete the children as well. Okay. So next, there is all external and will be all the nodes will be in the same level. So it may be having a problem. It will be having no failure of nodes also is available. Okay. We also consider this scenario when we are doing this kind of deletion process. Okay, if you consider m equal to 3, m equal to 4, so assume that is the m greater than 3. So following things will be inserted. Okay. So when inserting node is a overflow, it is a condition last one. It is a equal or flat or overflow. So such a things we have to adjust this sibling. Okay. So the adjacent sibling is not full. So move the dictionary and pair from the overflow node via parent. So to non-full adjustment sibling. Okay, this adjustment we can do done along with the your tree construction. So the adjustment sibling is not full means we have to move the dictionary parent to the overflow node via the parent. So to non-full adjustment sibling. This process will be needed when your node is the overflow. Okay. So this we called as an adjustment sibling. So if the adjustment sibling is full, split overflow nodes and adjustment full node and will be between the pair from the parent to get the three nodes with the floor. So m 2m minus 2 all divided by 3 and floor is a 2m minus 1 is all divided by 3. Same formula is available. So 2m divided by 3. Okay, so floor. So these are pairs. So two additional pairs of the insertion into the parent node. So this process will be when the node is overflow. When you are deleting a data, is the data will be overflow. If the data node is overflow, that again this adjustment sibling have to check with the along with the what problem, what formulas we have shown. This will be a red color in the my slide it's showing. So the floor. So the three different formula we can apply to check this kind of things. Okay, so clear. Okay. So then deletion process. So when combining the must combining three adjustment nodes and two in between the pair from the parent. Okay. So this is our condition. So total pairs involved equal to 2 into floor. Okay. So whole divided by 3. So along with the 2m minus 2 whole divided by 3 plus that is a floor of 2m minus 2 divided by 3. So minus 1. So that is the whole. So along with the plus 2. So we will getting the so 2 as pair values involved when we are deleting this kind of scenario. So it is a when combining the must three adjustment nodes in the two in between the pair from the parent. So it is a equals. When it is a equals mean that is a that floor is a formula will be changed. So 2m minus 2 so whole divided by 3 plus 1. Okay. So this all will be a important formulas to construct a tree. So this kind of questions will be going to ask in a gate questions. Okay. So because of that, I explaining this one. So next slide we're going to talk about that kind of questions only. Okay. The combining yield two nodes and a pair that is to be inserted. Okay. So two nodes that can be pair that is to be inserted into the pair. So that is the pair mean that is a two set. So okay, that is the one for the uh, parent node and then leaf node is inside of the parent node itself we having the pair. It's a leaf node itself the pair. So two things available here. One that we call as a pair is same level. So such a case that is a pair. So two nodes in the pair that will be inserted into the parent. So m that is a mode. So m means mode that is the equal to 3 equal to 1. This is such a case that is the m minus 1 pair such a ways we can include. Okay, or delete. So then is a mode 3 equal to 0. So node one node has a m minus 1 pairs and the other has a m minus 2. So such things we can use that is the m equal to 3 or 3 equal to 0. That is a mode value based you can delete and uh, data. So next 3 equal to 2. So node have with the m minus 2 is a pair. So like each pairs we having the m minus 2 means that is the m minus 2 ways you can delete that is when is a mode 3 equal to 2. So this way you can delete the combining yield values. So when you are having your pairs in the same level or maybe a same leaf. Okay. So this is the sample gate questions. Okay. So which one of the following statement is not correct? Say about the B plus tree data structure used for creating an index of your rational database or relational database table. These are the four answer they asked. That is the first one. Choice that is a B plus tree is the highest balanced tree. So second one is a non-leaf nodes have pointers to data records. So third one is the key values in each node are kept in the stored order. So fourth one, each leaf node has a pointer to the next leaf node. Okay. So anyone answer me? Try this one. Okay. So this answer is a B. So right. You are right. So answer is a B. So no leaf nodes have a pointer to the data records because the no leaf nodes have a pointer to the data record. That is a right one. Okay. So this person is a which one of the following statement is not correct. Say about the B plus tree. So data structure used for creating index in a relational database table. So that is the which one is a not correct. So non-leaf nodes have a pointer to the record. So leaf node is don't have a pointer because parent node only having the pointers. So first one B, I had the balance here is a right. So third one is a key values in the each node are kept in the sorted order. It's right. Next, each leaf node has a pointer to the next leaf node. This is also a right. So only is the wrong answer is a non-leaf nodes have a pointer to the data records. This is only a wrong one. Okay. So next question that is the sample question for this one. There's the gate question is the last 2018, I think it says this is asked. The following key values are inserted into a B plus tree. In which order of the following internal nodes is 3? So last slide only we have discussed. The last slide only we have discussed this one is when is a m equal to 3. So that against leaf node equal to 2, then sequential given below. The order of the internal nodes in the maximum number of the tree pointers in each node, and the order of the leaf node is a maximum number of 2 items that can be stored in it. So B plus tree is initially empty. So these values are 10, 3, 6, 8, 4, 2, 1 in this order. The maximum number of times leaf node would be get splitted as a result. This insertion is so how much? The options are 2, 3, 4, and 5. You all know that is the already internal node is a 3. So automatically how many things will be inserted? That is insertion is resulting in splitting. How many splits are available in the leaf? These are 3 splits. That is the answer. So that is m equal to 3 values. That is a thing we have to know from this example problem. So like that is a lot of problems they're going to ask. Okay. So mostly deletion insertion problem will be asked. Okay. 2014 and 15 I have attended this exam and cleared the grade. So such the same time that is I have followed this kind of questions preparation. I got clear. So same thing you can follow that you can clear easily. So it is not a biggest thing to clear this kind of questions. Okay. So see that is a B plus tree. So 9. So root node. So indexing or insertion, deletion we have seen. So I have to summarize once again this all the things what we discussed. Okay. So that see that as I want to summarize first I displayed that is a disk-based storage system. What are the consideration for? What are the access method? The following sequential access method, MB search tree, B plus tree. Then how that is your data layout of your disk will be a track sector, will blocks are defined. So I explained this three concept. Then followed by what are the access time of the disk block, seek time. So how seek time is calculated. What is called latency? How latency will be calculated? What is the transfer time? How this transfer time is calculated? So they considered for a disk-based dictionary structure. So how it is because of n is working and AVL search tree is working. What is the disadvantage of this? Why we are going for a new tree that is a B plus tree? It will be following the M-based search trees. Okay. So then I explained the B plus. Okay. So it is following the same thing as a B tree. So what is I, what is J, what is A, what is a K, and I explain. So that is a dictionary pairs will be a leaf only. Leaves from the double linked list we are following. So then the if you call it as in B tree, example with the M, so shown how it is a tree will be considered. Okay. So then that is the example for the B plus tree I explained. So index node, what is index node, what is a leaf and data node. So how is a tree will be a constructed. So then after the construction we have to search the based on your key. So these are key values of file means it's going to search the values based on the key. So that is in between what is the values available. So 6 and in between the 20 it's going to search. So key coming between the 6 and 20 is a 5 is the value, so it is going to search that. So that is the inserting of values if the 10 means, so is how inserting. So how it is a two value pairs or maybe insert a pair by 2, so it's going to do that. Okay. So next insert a 3 node. So insert a new pair, so that is a key in the ascending order. So ascending order means the sequential format we following. So because of that, the sequential order is made so that we can put it in the sequential order. So inserting a 2 plus and 2 plus pointer into the parent. So then followed by the if the 18 means how the inserting a 18 into your left hand the parent node. So inside of the leaf node. So that is the insert entering the 17 plus pointer into the parent. So then it is a make it that is 17 and 16. So that way that is it. 16 and 13 is available in the parent, so there is a two parent will get divided. So in around the 16 is a parent node, 9 and 16 will be a so leaf node for this 16. So 30 for this another parent node. So here 16 is available another node means now that is a leaf node will be a 17 and 18, 13, 40 will be taken. Okay, yes, a leaf node. So now there is a key pair will be deleting a 16. So that is the way deleting this from this one. So that is it is deleting pair values of the leaf. Okay. So same thing that is a 1. Same thing that is a 7 and 2 will be deleted. Same thing that is a so delete the key pair will be a 2. So merge with the sibling. Okay. So then followed by 3. So one by one we are deleting same procedure. Sequential order we are deleting. Okay. But the same thing is the following: the index node becomes a deficient. So get that is the greater than or equal to one from the sibling. So move last one to the parent. So get the parent key. Okay. Okay, see this is a merging index nodes and different merge data nodes. Okay. So this is the formulas. Using this one, we are going to calculate this of 4. So then still, this is the m equal to 3, m equal to 4. Assume m greater than or equal to this of following. So insertion operation. So this insertion means we following this one. So deletion means we following these formulas. So last one is in sample questions. Okay. So this I think you understand of the B plus tree. Okay, this is a very easiest topic, so you can score well. So mostly this question they ask that is a two or three questions are minimum one question may be coming from this sequential order. So because this is one of the important advanced method available. So from the database management system, this is the important area. So you consider for this kind of tree or hierarchical or maybe a access method to get a score. Okay. So minimum one or two mark you will get here easily if you have studied this kind of concept. Okay. So clear. So another one that is it is a implementation and understanding of this kind concept is a very easy compared to the other method which is available in the database concept. So it's concentrate this thing. So it also if you are trying to do this highest scoring person, so you concentrate more on this. Okay. To take it to this some another one questions. Okay. So So see this example. So delete pair with the key equal to 3. If they asking, now that is asking is a 5. So I want to delete a pair with the key 5. So I want to delete a leaf node 5, then only root node 5. So sometimes is a confusion may be arised. So such a way, first you in this hierarchical order is a left hand child that is the your 5 is available, pair node is a 5. So that is a 5 is first deleted from this pair, then it's a 5 deleted, then it's going to 6 will be a now it's a considered as a your parent node from this root node 6. So this is very important. If the key value will be a 6, so sequential order only we can do this process. Okay. So this is the another one if you are doing. So this is a critical one. Okay. Another one that is see this here that is a 9 and 9 in this will be same. Okay. So if the index node becomes deficient, so such a case, so that so this 9 will be a consider for this kind left hand side. So now that is at this side child left hand side child node 9 or maybe leaf node 9, it will be a if your deficient will be erased in the index node, so 9 will be a considered for the your right hand side root node, right hand side parent node. First parent will be 9. So this is, if the deficiency comes, that will be applied over here. Okay, so clear? Any more question? Put it in the chat box. If any questions, raise your hand. Okay. So I am seeing your chat box. Okay, it is available here. So that is the your question is understandable. So that if the form in that m value it's a 4. Okay, so I explained 3. If the m value is a 4, how it's going to react? So that is the at the m value 4, the B tree allows nodes with the degree 2, but is the m plus needs to the degree 3. Assume that is the greater than 3. Further things will be available for the your right hand side or the left hand side. So flat road need to support the insert and delete and improve the worst case search time at the expense of insert delete. So it is useful when searching is uh, available in the dominant operation. Okay, so that insertion will be getting very easy. If it is node is overflow, then only is a adjacent sibling is not full. So move the directly parent to the overflow node. So via parent and non-overflow adjacent sibling is implemented. So for this kind of scenario. Okay, so clear. So I think you all understand the concept. Okay, so very simple thing. Okay, that is one of my professor. So why I'm studying. So they use the CUP concept. You all know that. Okay, so concentrate, understand, practice. Okay, okay, that is concentrate on the work logic. So what mechanism or what the procedure, what is the formula they using. Okay, so then concentrate. Okay, then what they understand the concept, then practice. So this will be a only practice only we can clear this kind of exams. Okay, so if you understand that, you will not practice on this concept, you cannot get a correct answer at last. So that practice on that, on your concept, and do practice every weekend or maybe when you are having your time. So this kind of formulas, this kind of sample questions, this kind of the concepts, then only you can clearly identify and understand and concentrate on the your concept, and can you practice on the concept, you can clear this exam. Okay, so very simple. Okay, I think this is the time to leave. So if you're having the more doubts or more need of your knowledge from this topic, you can contact me anytime. Okay, so feel free to contact. So I'm available in the department only. Okay, so this is the way you can use the B plus tree. So a lot of application they developed, a lot of concepts they developed in this concept. So you refer the a lot of materials are available in the online. So as well as your resources are available for the grade. Okay. So if you are unable to find anything, so you can come up to me. I will clear the doubts up to my knowledge. Okay, we can share the knowledge. So you also grow. Myself also growing with this concept. So this is the ultimate aim of this class. Okay, so get clear the get and get a good marks and get a good college. So this is the my side view. Okay, thank you all for attending this class. Okay, so I will come again for the next class. Thank you for participating.